Okay, guys, in this lesson, we're going to take a look at exponential functions and how we are going to identify them in a graph, in a function table, and how to identify the key features as well as write the exponential function as an equation. So first of all, let's just talk about the characteristics of an exponential function. You can see here that we have a exponential graph. This is considered the parent function. It's the most basic exponential function. And we're going to start out with this lesson simply writing exponential functions in the form of f of x equals a b to the x. So later we will discover there are other components to our functions, but for now we are just going to have f of x is equal to a b to the x. Now notice that our input value is the exponent. That's what makes this an exponential function. So let's talk about the a. So in your notes, make sure that you write the a value is the coefficient of our exponential factor here. So A is considered the initial value. And when we get to word problems, this will make more sense. But your A value is the initial value. Our B value in an exponential equation, this is our growth factor, and it's also our decay factor. So we will talk about this later in our lesson, whether it's a growth or decay, but it is the factor. So we have our initial value multiplied by our growth or decay factor raised to the exponent of x. The other thing about an exponential function in the graph is that every exponential function has an asymptote. So our asymptote in this example is y equals 0. So we always write our horizontal equations as y equals, and then whatever value it passes through on the y-axis. So an asymptote is simply a line that our graph approaches, but it never reaches nor touches the asymptote. So this blue line is our exponential function, and it gets very close to the asymptote of y equals 0, but it never touches and it never crosses. So that is an asymptote. And again, every exponential function has an asymptote. Okay, let's just take a look at our linear function, f of x equals 2x, and then we have our exponential function, f of x equals 2 raised to the x. So remember, we typically write linear equations in slope-intercept form, y equals mx plus b. In this case, we have a slope of 2, and our y-intercept, the b value, is 0, 0. Now, let me make sure that you do not get confused with this b variable and the b variable, the base of our input values. These two b's are two different values. So in our linear function, we can see that what the linear and exponential function, what they have in common is that there is an interval of increase. So from negative infinity all the way to positive infinity, we have an increase. So this function is always increasing and there is no interval of decrease. The same for this exponential function. It is always growing. This example is always increasing. So our interval of increase would be from negative infinity all the way to positive infinity. It is increasing and it does not have an interval of decrease. This graph is constantly increasing and it's never going down. And then we have in behavior, and again, we have a left and a right side of our graph. So for this function, this linear function, as x approaches negative infinity, f of x approaches negative infinity. And then we have as x approaches positive infinity, f of x approaches positive infinity. Now let's compare that to our exponential. With exponential, what's going to come into play is the asymptote. So I always like to write in the asymptote. So again, our asymptote is y equals 0. So this time, as x approaches negative infinity, f of x, the end of the graph, approaches 0, the asymptote. And then on the right side, as x approaches positive infinity, f of x approaches positive infinity. It goes up. So with exponential functions, when you're dealing with the end behavior, you will always use the asymptote in part of your end behavior. The other thing that is a little different, the range is going to be different. So for this linear function, the range, which is our y values, is going to be from negative infinity to positive infinity. So it continually goes down, it continually goes up. But the range for this exponential, remember, range is how far down, how far up. So the range, this graph is getting close. It goes down to 0. It does not touch 0. So we will use a parenthesis, and then it goes up forever to positive infinity. So with exponential functions, you will use the asymptote in end behavior as well as the range. Now let's move on and take a look at two function tables. We have a linear function table and an exponential function table. So what's super important to know the difference is in a linear function, you have a constant rate of change. So our x values are increasing by 1. So we can just focus on the output values. How am I going from 2 to 4 and 4 to 6? Well, we are adding 2 each time. So there is a constant rate of change. The change is the same, it is constant. However, on exponential functions, it's more of a constant ratio. So how am I getting from 2 to 4 and 4 to 8 and 8 to 16? Instead of adding or subtracting to get from output to output, we are multiplying. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. And we could get a 6 point and multiply 32 times 2 to get 64. So our output values are changing rapidly compared to a linear function. So exponential functions increase or decrease at a rapid pace because you are multiplying to get from term to term. The b value is that multiplier. So when we have our basic exponential function, f of x equals ab to the x, a is our initial value, b is the multiplier, it is the base of the exponent x. So this is the multiplier. This is how we are increasing or decreasing. So to find the b value in a function table, we can compare, we're going from 128 to 64 to 16 to 4 to 1. So the best way to identify that b value is to take a output value and place it over the previous to make a ratio, because our b value is the common ratio. And then I will have 16 over 64, and then we will have 4 over 16, and then we will have 1 over 4. And so these all simplify to 1/4. So this is the common ratio. This is our b value. So if I were to start writing the equation, 1/4 would be our b. These are decreasing by 1/4. So that is the pattern there. Now let's take a look at another example. So we're going from 8 to 24 to 72. We can see we're not adding the same thing, so it's not linear. So again, we just take an output and place it over the previous output, and then we will simplify. And of course, you can absolutely use a calculator. So this gives us a b value of 3. So the b value in this exponential function is 3. We are multiplying times 3, times 3, times 3, times 3. This is growing where this table was decaying or decreasing. Okay, let's take a look at a few of these and determine if it's linear or exponential. So I can see, and again, we're just comparing outputs. I'm going from 2 to 4 to 6 to 8 to 10. So I can see that I'm adding 2 every time. So this is going to be linear, and this would be my slope. I would have a slope of 2. Our next one, we're going from 8 to 16 to 32 to 64 to 128, and we can make all of our ratios like we just learned, but we can easily see that we are multiplying times 2, times 2, times 2, times 2. So this one is an exponential function, and the b value, the multiplier, the base is 2. Okay, our third example from 3 to 6 to 9 to 12, it looks like we are adding 3 each time. So that has a constant rate of change. So this is a linear function where our slope m is 3. In our fourth example, we have 2 to 4 to 8 to 16 to 32. This is multiplying. So we know this is an exponential function with a multiplier, a b value of 2. And then we have 64 to 32 to 16 to 8 to 4. So I am decreasing, and it is decreasing by multiplying by 1/2. So I can see that. So this is exponential, and our b value is 1/2. So this is decreasing. This will be a decay. Then we have 3 to 9 to 27 to 81 to 43. So this is multiplying to get from output to output. So this also is exponential with a b value of 3. Okay, now let's take a look at, here's our basic exponential function, and we are going to graph this by hand. We're just going to do a few of these. So we're just going to plug in -2 in for our x. And so when we plug in, don't forget that the negative tells me we have a fraction. We reciprocate this and we get 1/4 as our output. And then when we plug in -1, we're going to reciprocate this 1 over 2 to the positive 1. So we have 1/2. Then when we plug in 0, anything raised to the 0 is 1. And then when we plug in 1, 2 to the 1 is 2. And then when we plug in 2 for x, 2 squared is 4. And now we're going to graph this. So we have -2 and then 1/4. And then we have -1, 1/2. And then we have our y-intercept, 0, 1, and 1, 2, and 2, 4. And we could even plug in 3, and that would give us 8. So we can see that our graph is increasing. It has an interval of increase, and it gets closer and closer to the asymptote. The asymptote again here is y equals 0. Okay, so now let's just talk a little bit about our key features. Now, guys, when you just have f of x equals 2 to the x, your a is an understood 1. The b value is the base of x, so it is 2. So we have -infinity to positive. Our graph is going forever left, and it's going forever right. I'm going to go ahead and write in y equals 0 for the asymptote. The range, it goes all the way down to 0, but 0 is not included, and then it goes up forever. The y-intercept, I'm going to write it as an order pair, 0, 1. The interval of increase is -infinity to positive. There is no interval of decrease. And then as x approaches -infinity, f of x approaches, it's getting close to 0. As x approaches on the right side, the graph goes up. Our asymptote is y equals 0, and then the AROC. So between x being 0 and 3. So when x is 0, I have this point, and then all the way to when x is 3, I go up here. So we are looking for the slope between these 2 points. So it's up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3. So our AROC between that interval is 7/3. Okay, now let's take a look at where we have a base that's 1/2. And so when we plug in -2, we reciprocate and we get 2/1, or just 2 raised to the 2, so that's 4. And then when we have 1/2 raised to the -1, we reciprocate and we have 2. Whenever we plug in 0 as an exponent, it's always 1. And then when we plug in 1 for x, we get 1/2. And then whenever we plug in an exponent of 2, we get 1/2 times 1/2, which is 1/4. So we have -2, 4. We have -1, 2. Our y-intercept, 1, 1/2, and 2, 1/4. And this time we have a decay. So our graph has an interval of decrease. It never touches or crosses our asymptote here, y equals 0. So again, this has an A value and it's the understood 1. My base, my B for base is 1/2. And our domain, it goes forever left and it does go forever right. Our range, it goes down to 0, it's not included, and then it goes forever up. And then our y-intercept, we're going to write as an ordered pair, 0, 1. There is no interval of decrease. This graph is, there's no interval of increase. This graph is always decreasing, and it decreases across the entire graph. Our end behavior as x approaches -infinity, so as we go to the left, f of x, the end of the graph, goes toward positive infinity. Then on the right side, as x approaches positive infinity, as my x values get greater and greater, the output values approach 0, the asymptote. Our asymptote is y equals 0. This time we're finding the average rate of change, the slope between x being -3. So when x is -3, y is 0. And then when x is 0, y is 1. So this time we have a negative slope. So we're going down 1, 2, 3, 4, 5, 6, 7. And then to the right, 1, 2, 3. So we have -7/3. Okay, so now let's just take a look at what makes a function a growth or decay. So it's all about the b value. So when your b value is greater than 1, we have a exponential growth factor. So when b is more than 1, it is going to increase. When b is between 0 and 1, let's not say a fraction because 7/2 is a fraction, but that would be a growth. A decay is when the b value is between 0 and 1. This is when we have an exponential decay. So make sure you get this in your notes. Growth factor is when b is more than 1. Decay factor is when your b is between 0 and 1. So you can see here that our graph is increasing. So this is a growth. And this one is decreasing. This is a decay. And you can see in both of these, the asymptote is y equals 0. Now the asymptote, it's not always y equals 0. Just for this introduction, it is, but that will change. If the graph shifts up or down, the asymptote also shifts up or down. Okay, so without graphing, we're going to determine if it is a growth or decay. So our first one, f of x equals 3 times my b value, 4/5 raised to the x. So 3 is the A value, that's your initial value. Our multiplier is 4 over 5, and because this is between 0 and 1, this is an exponential decay. Number 2, our A value is 2, but the B value is 5 over 4, which is more than 1, so this is a growth. Number 3, we have an initial value of 1/2, and our multiplier, our B value, is 1/6. That is between 0 and 1, so this is a decay. And then number 4, we have an A value, an initial value of 2 over 3, and it's the B value that tells us if it's a growth or a decay, and this is more than 1, so this is an exponential growth. So this looks like this one goes down, grows, and decays. Okay, the last task is to be able to write an exponential function only in the form of f of x equals ab to the x. So we have learned how to find the multiplier, the b value. How are we getting from term to term, or I should say output to output? So we can see that this is a decay, and we can find that common ratio, which is going to be 1/2. So our b value is 1/2. To find an A value, we can simply use any of these points to plug in for x and f of x. I'm just going to use this first one. So we have our output is 64 equals A times 1/2 raised to the first. So then we have 64 equals 1/2 A. We are going to divide by 1/2, which is simply multiplying by 2. So our A is 128. So we can put that all together. F of x equals 128 times 1/2 raised to the x. Okay, let's find the B value. So from 2 to 4 to 8, we are multiplying by 2. This is our B value. So f of x equals A times 2 to the x. We're going to pick a point. We can just pick this first point. So f of x is 2. We don't know A, and 2 raised to the first. So we have 2 equals 2 to the first is 2 times our A. Isolate your A, and A is 1. So we have f of x equals 1 times 2 to the x, or just 2 to the x. And our last one, 3 to 9 to 27 to 81, that is being multiplied by 3. So that is your B value. So we're going to write what we have. We don't know A. Our B value is 3. We're just going to pick, I just like to pick the first point or a small values, plug in 3 for f of x and 1. And then we have 3 equals, that's going to be 3A. Isolate our A value, and we have 1. So we put it all together, f of x equals 3 to the x. And if you want to write the 1 in for the A, that is fine, but it's not needed. So remember, find your B value to see what the multiplier is, and then choose one of the points to plug in for x and f of x, and then just do your algebra to find the A value and then put it together. I hope this helps.